Okay, give me 1 second. Like I said, I'm gonna share today's material now. Okay, so I need everyone to confirm if you're seeing today's material. Are you seeing multinomial distribution? Or is everyone seeing this now? Multinomial distribution. Okay, thank you so much. I want to welcome you to today's material. We are still on deck 5, and this is a multinomial distribution. But before I get started with this material, I just want to inform you that the student rating of professor that we call the SRT is already released. So you need, as required by the authority or in the university. So, very close to the end of the semester, they expect students to complete student rating of professor. Okay, the university actually want to hear from you about the way we are doing our work. Okay, so I'm using this opportunity to inform you, you are required to do that. You can actually, you can see that at a section on Canvas. Make sure you complete that. Okay, so I want to welcome you to my lecture today. We call this multinomial distribution. And let me just tell you, multinomial distribution is a generalization of binomial distribution. And don't forget, binomial distribution is also a generalization of Bernoulli distribution. I'm going to remind you now. Okay, I'll quickly remind you, Bernoulli distribution, we actually use that in statistics to model, events that have two possible outcomes. Okay, I'm going to say that again. We use Bernoulli distribution to model events that have two possible outcomes. So when you perform an experiment once, maybe you have one trial, okay, and there are two possible outcome. Of course, we actually going to use Bernoulli distribution. Now, situation whereby the numbers of trial is more than one, and we still have two possible outcomes. We basically have binomial distribution. But let me tell you now, for multinomial distribution, what we are trying to talk about is more or less that we have a generalization, okay, of Bernoulli and binomial distribution. And that's exactly what you are seeing here. Okay, so the idea of a matrix, the idea of a vector will be used because we're talking about generalization. So take a look at this guy now, a random vector x1 up to sk. Okay, it's called multivariate Bernoulli. Let me tell you this, multivariate. Why is it called multivariate? It's because look at this guy, follow Bernoulli, x2 follow Bernoulli, and sk follow Bernoulli. You have number of x, here is k, and of course that particular vector now actually follow multivariate Bernoulli distribution. And don't forget, the component are 0 or 1 value and sum to 1. Okay, now situation where we have this, then we're going to have what we call multinomia. That will be called multinomia. Okay, multivariate Bernoulli distribution is actually multinomia. Now you remember the other time, the expected value of, if x follow Bernoulli distribution, the expected value of x is going to be p, right? But situation where we're talking about multivariate Bernoulli now, okay, if the x1 follow Bernoulli, the mean expected value of x1 is going to be equal to p1, s2 follow Bernoulli, the expected value of x2 equal to p2. But in a situation where you have a vector x now, where it comprises of x1 up to sk, then if I'm focusing on a vector x, the expected value of a vector s is basically going to be that guy, which is actually called the probability of sources. Okay, and that very p here, I'm denoting the whole of that as p. So I wanted to say this very p here is a vector because of the fact that it comprises of several p's. Okay, so that is what we call the mean of a multivariate Bernoulli distribution. Okay, so I just want to return to Bernoulli, with xi follow Bernoulli distribution with the parameter pi. Okay, the expected value of si, equal to pi, and the variance of si equal to pi into 1 minus pi. You know this from Bernoulli distribution. And let me tell you this, if I want to find the covariance, the formula for covariance is equal to that. And in a situation where the xi and the sj equal to 0, and the meaning, if the xi and the xj equal to 0, what are you trying to say? We basically trying to say that the covariance will be equal to situation where they are not independent. I mean, where xi and sj are independent, you expect the covariance to be equal to 0. I think you understand that, right? Okay, but in a situation where the product now is 0, okay, that was why I said, but the component of x are not independent means they depends. Okay, where I not equal to j, we have xi sj equal to 0. You know what I mean here. Okay, we are xi not equal to j. Okay, we have this si and that. So in that situation, this guy is basically going to be 0 in that. And you know what? If this guy is pi, okay, this guy is pj, right? Okay, don't forget the expected value of si equal to pi. Because of that, with that multiply, then with the minus, I'm actually going to have that guy. So which means the covariance of xi xj equal to minus pi pj. And let me tell you this situation where covariance is not 0. I'm going to say that again. Situation where covariance is not equal to 0, then what I mean is that xi and sj are not independent, because they're only going to be independent if the covariance of xi and sj is equal to 0. But right now we got it minus pi pj, which actually means the si and the sj are not independent. Okay, I just wanted to take note of that. Now we actually want to use this now to generalize on the multinomial distribution. We are x here. Don't forget, x is a vector. Okay, x is a vector. Okay, expected value of s is going to be equal to p. P is also a vector. Okay, don't forget your p is actually p1, p2 until you get to pk. Okay, and your x is actually x1, x2 until you get to sk. Don't forget. Okay, they are vector. You get what I mean, right? Okay, now if I want to talk about the variance of x now, don't forget x is also a vector, right? Okay, the variance of x, this is what we're going to do. If you come back here, okay, let's assume that this guy is this, and this guy here is this. If I want to rewrite the covariance matrix now, I can basically write this guy here. P minus P times transpose of that. Take a look at that. Okay, that is if I want to write it in matrix form. Okay, I just want to take note of that. Okay, so I think based on what you've done before, don't forget that we're using the idea of linearity of expectation. You know, if xi, if x1, x2 up to xn, IID, multivariate Bernoulli random vector. Okay, if I want to add all this together now, x1 to xn, which is this guy now, of course, the resulting distribution is basically going to be a multinomia. Okay, the resulting distribution is going to be a multinomia. Okay, the multinomia with a sample size of n with a success probability vector. Don't forget, that is not just p. That's a p1, p2, up to pn, depending on the number of x vector. I want you to take note of that. And you know what? To take a look at this guy now, that is that's an abbreviation for multivariate distribution with parameter n and p. Don't forget here, p is a vector. Okay, p is a vector. I think a chat came in. Somebody said, does the vector p look like something like 0, 0, 1? Yeah, it look like that. You are right. You know, let me just say, what look like that is not p. It should be x. Okay, you know, somebody shared with me and said, does the p look like 0, 0, 1, 0? No, what look like is 0, 0, 1, 0, 0 is going to be x, not p. P is a probability. Okay, p is a probability. And you know what? We don't consider probability equal to 0, probability equal to 1. That's an extreme case of probability. But it is a random variable x that can be 0 or 1. Why do we say 0 or 1? Because it has two nature. You know, there are two possible outcomes. Okay, one level of the outcome is going to be coded as 0. The other level of the outcome is going to be coded as 1. Until you get that. Okay, now that is what we actually wanted to know about. So in generalization now, okay, if I want to use the linearity of expectation, I'm going to say the expected value of y, where y is a vector. Don't forget y equal to sum of x1, x2, and so on like that. Then the variance equal to, you know what I'm using here? I'm using the linearity of expectation. Don't forget the variance of the sum is going to be equal to, if all the variances are the same, you multiply it by n. If all the means are the same, you multiply by n. I think you remember what we did before. Okay, so I just wanted to take note of that. Now, the next thing I want to talk about now is looking at, you know, we want to find the PMF of a multinomial distribution. Okay, now, if you want to take a look at this guy, that is the probability of Sj equal to small Sj, like you want to find what is the probability of x1. Maybe you want to find this probability of x1 equal to small x1, probability of x2 equal to small x2, probability of x3 equal to small s3. Okay, dot 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 until you go to xn equal to that. You know, we always want to find what is the probability of a random variable equal to a realized value. And you know what? We're actually going to use the idea of independence. If we are zooming x1 up to xn are independent, you remember what we did before. Okay, the probability of the joint. If x and y are independent, the probability associated with the joint is basically going to be a product of the marginal. You get what I mean, right? And that is what I'm actually using here. Okay, this guy here is a symbol for products. Okay, it means what I'm actually doing here, I'm actually multiplying the probability, you know, this multiplied by the probability of x2 equal to small x2, okay, multiply until I get to the probability of xn. Okay, so what am I trying to do? I'm using the idea of independent. The probability of the joint is basically going to be equal to the product of the marginal. And you know, in statistical theory, you know, this is a way to write the product. Okay, and you know what? Don't forget, each of these probability, okay, is actually p. You get what I mean? Now, because of that, okay, we're basically going to say, okay, p high raised to power y high. Okay, I wanted to take note of that. Now, where we're driving at, we want to look at the formula for multinomia. Okay, now this formula is part of binomial, right? Okay, in binomial distribution, where you are actually choosing y out of n. Okay, in the end, what I'm going to show you now, you're going to see what the formula is going to look like. This is a formula now. This is a multinomial. That's a probability mass function of a multinomial distribution. Don't forget, the multinomial distribution is a discrete random variable. Okay, take a look at this now. N combination y, and you got a product. Take a look at that. You got a product of the probabilities. You got a product of the probability. That's exactly what you have right now. Take a look at this. How is this guy different from binomial? Okay, if you look at binomial, if x follow binomial with parameter np, okay, the f of s is going to be n combination x, p raised to power x, okay, and 1 minus p raised to power n minus x. That's binomial. Okay, but this is multinomia. Okay, the multinomia is basically going to have different more than two probability. That's why you see PI. Take a look at that. Okay, now I quickly want to move. I think what I'm gonna do, let me give you an example. If you basically want to use that formula now, okay, I'm gonna give you an example of that. Okay, I'm gonna share my whiteboard. Give me 1 second. I'm actually and I needed to confirm if you are actually seeing my whiteboard. Are you seeing my whiteboard? Is everyone seeing my whiteboard? I needed to confirm. Okay, thank you so much. Now I'm gonna give you an example of multinomial now. Okay, let me write that example. Okay, so three card players. Okay, three card players play a series of matches. Play a series of matches. Okay, 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 the probability that player one, the probability that player A will win any game, okay, will win any game is 20%. Okay, the probability, okay, the probability that player B, okay, that player B win is 30%. Okay, and the probability, okay, the probability of player C, okay, win is 50%. Now here, instead of each of them, instead of player A win or loses, or player B win or loses, or player C win or loses. Now, because we have more than two now categories of these players, right? Okay, we actually going to use multinomial. Now, the question now, based on this probability now, okay, what is the what is the probability that player A, okay, now if the player A, okay, win one game, okay, B win two games, okay, and C win three, and C win three games if they play 6 games. Look at that. you already know their probability. Okay. Now, if they decide to play 6 games now, what is the probability that, hey, we win 1 game, B, we win 2 games, C, we win 3 games. Don't forget, they agree to play how many games? They actually agree to play 6 games. Okay, you can take a screenshot of this. Okay, if you have taken a screenshot or you taking this example, I need you to say yes or you comment yes, because I want to I want to clean that up. And okay, thank you so much. I'm actually um gonna clean that. I'm gonna clean that up now. Give me 1 second. Okay, so if I want to use the you know the other time, okay, I actually said if you the PMF that actually go for for multivariate, for multi, okay, variate NP, okay, I said f of y is n combination y, okay, pi, that's a product, right? I start from 1 to that, and pi, it is super y high. Okay, and here I actually start from that to that. Okay, now if I want to rewrite this guy, because this formula now, because my k will be equal to 3, I have just 3 players, right? In this, I have 3 players. Okay, now if I want to rewrite my probability formula, okay, I'm actually going to write n factorial divided by, okay, if you look at what I'm gonna actually write now, so y1 factorial, y2 factorial, y3 factorial, then I'm actually gonna have p1 raised to the power y1, p2 raised to the power y2, p3 raised to the power y3. Look at that. If I want to, because I got 3 players now, okay, my PMF is going to become that. Okay, now if my PM is actually going to become that, so what do I want to find? I actually want to find the probability that A will win 1 game, B player will win 2 games, and C player will win 3 games if they play 6 games. Now, what is my end? My end is going to be 6. They want to play 6 games divided by Y1 is the number of games that player A will win, Y2, the numbers of. So what I'm actually trying to talk about here, give me 1 second. What I'm trying to say here is that I basically want to find the probability, or give me 1 second, the probability of Y1 equal to 1, Y2 equal to 2, and Y3 equal to 3. Okay, that's what I want to find. So I'm going to have 1 factorial, 2 factorial, 3 factorial. You know what I'm going to do here? What is the probability given initially for A to win? Okay, the probability given for A is 0.2. Okay, 0.2. You're going to raise it to the raise to power 1. Where do I get 1? Which is that if A actually win 1 game, okay, and what is the probability that B is basically going to win 30%? That will be 0.3, and that will be raised to power 2. What is the probability that I'll say is basically going to win? That will be 0.5, right? Given in the question, 50%, and that will be raised to power 3. All what I just need to do now is to simplify this guy. Okay, when I simplify that guy, if you solve that very well, you're basically going to have a 0.135. That's going to be the final answer. Take a look at that. So I think I just walk you through now how to use a multinomial distribution to figure out probability problem. Okay, we use multinomial distribution in a situation where we got 2 possible outcomes, and when we get 2 possible outcomes, we have more than 2 categories. When you have 2 categories, you got binomial distribution, but right now you got 3 categories, you can see, and that is why our k equal to 3. Get what I mean, right? Okay, if you get that, my explanation explanation now, I need you to say yes or you comment yes. If you get my explanation now about how I figured that out, I need you to say yes or you oh my God, thank you so much. Okay, I'm so excited that you get it right. Okay, I'm gonna go back to the material. But you know what, in case you don't really understand, please, you need to ask me a question. You pay for this service and you deserve to be served better. Okay, so I think I just work, what I'm just trying to say here for binomial, that is what we have, a special form of that. So if a random scalar x followed by binomial with NP distribution, then the random vector x comma n minus s have a multinomial distribution. And don't forget where p equal to this. Don't forget p here is the probability of success and 1 minus p here is the probability of failure. I just want to take note of that. Then I'm actually going to move now. Okay, I think I just explained this to you. This is adding y1 up to yk. Okay, so we adding that together if all of this equal to n. Okay, because what we're trying to say is that the other time we're trying to say we partition in the example that I cited the other time when I was talking about having, give me 1 second, 6 factorial divided by 1 factorial, 2 factorial, 3 factorial. You know what I mean? When I had 1 to 2 to 3, that must be equal to 6. And that is what I'm trying to say right here. Adding y1 to yk, that would be equal to n. Don't forget in the last example, n equal to 6. And each of the of these, by the time you add them up, that should be equal to 6. Okay, that is exactly what I mean. And you know what? If that happened, okay, if I want to find y1, it's just going to be n minus the rest. Okay, so take a look at that. Okay, so I basically want to move to something serious. This is another example. Okay, this is an example in politics now. Okay, what is true? You look at the category here, you got Obama, McKay, Barr, Nada, and other. You got the fact, in election, it's either Obama wins or not. It's either McKay win or not. It's either this guy wins or not. Okay, so, but because there are more than 2 people, okay, it means we can use the idea of multinomial can actually be used. You get what I mean, right? Okay, so here, if you collapse like maybe, because when you take a look at this from bar to nada to order, what they have is not significantly measure up to what Obama and McKay has. Okay, to the best of my knowledge, Obama happens to be the former president of the United States. And I think Obama and McKay contested for presidential election one period of time like that in the United States. You get what I mean? So when you combine all this with this, of course, you have this guy, right? Take a look at that. And in such a way, when you add the probability together, it must be equal to 1. Idea of multinomial can actually be used here. Okay, so I think I basically want to move to something else. How do we find marginals in multinomial distribution? Okay, I want to move into that now. Okay, don't forget if I'm actually having, if you consider the marginal distribution of yj plus 1 up to yk, okay, of course, you remember what we did the other time. Like if I have a joint, there's a way we can figure out the marginal. We're only going to sum the joint with respect to the variable we're not interested in. If that's a discrete, if it is continuous, we're basically going to integrate, right? We're going to integrate the joint with respect to the variable we're not interested in. Now, if I have a random vector z, which is actually this guy, and which has a multinomial distribution with this where q equal to that, okay, now we can decide to figure out what the marginal is going to be. So here we're trying to figure out the marginal of yj plus 1 of the yk in two different ways. Now, if you want to figure out that, we're going to define w equal to the y1 plus y2 up to yj. Don't forget, take a look at this. Here, y1 start to yj. It's like you're having y to y9. Let's say you have y1, y2 up to y9. Just assume that. And look at this one. Maybe this one is now starting from y10, y11, and so on like that. Take a look at that. So, and that was why if you take a look at the y1 up to yj, but we are seeking, we want to consider the marginal of yj plus 1. You know, these guys stop at yj, but if we want to start from over that, look at that. Okay, so if I want to find the f, if I want to do that now, I need to first look at the joint. This is the f of w, where the w is from y1 up to yj, okay, and comma yj plus 1 up to yk, which is this guy here. Don't forget, if you look at the entire thing here, it's basically going to be from y1 to yk. It's more or less that you are partitioning that into two, right? And that was why we say two different ways. We are partitioning that into two. So if based on this now, if I want to write our multinomial distribution, is going to be n. Don't forget, take a look at this. These are two entities. So it's going to be n combination w and the rest. Look at that. You remember the formula of multinomial, right? And another, then the p1 up to pj raised to power w. Why do I have p1 up to pj? Don't forget w is y1 up to yj. You remember if the expected value of w, okay, is basically going to be p1, w1 is going to be p1. So if you look at the expected value of w now, you're actually going to have p1. Take a look at this. The expected value of w is going to be p1 plus p2 until you get to pj. Don't forget, each of that is Bernoulli. Okay, if I take the expectation of w, you remember the linearity of expectation. That was how you get this guy here. Now raised to power w, okay, and the rest of this guy, okay, we actually carry that. That's why you have that. Take a look at that. So this is a multinomial, okay. Now since w, you know, w here, okay, is basically going to be n minus this, okay. W is going to be, because don't forget n, what is my n? N is basically addition of all of that, y1 plus y2 until we get a yk, okay. And don't forget y1 plus y2 until you get to yk is being partitioned, okay, into you partition this into y1 plus y2 until you get to yj. I mean, until you get to yj. Give me 1 second. This is what I'm trying to say. Don't forget the other time I said this is y1 to yj. This is yj plus 1 to k. If I add all of that together, that would be equal to n. Okay. Okay. Y, which means it's going to be y1 up to yk. Okay. Now, if I want to find maybe a w now, I'm basically going to have that. Where is going to be w going to be n minus yj plus 1 up to yk. Don't forget the w itself here. The w itself here is basically y1 to yj. And don't forget y1 to yj plus 1 up to yk is going to be n. So take a look at that. Now, if that is what I have, I want to find the f of, don't forget, that's what we want to find from the beginning. We are seeking to get the marginal distribution of that, which is going to be that f of j, yj plus 1 up to yk, okay? And that is basically going to be this guy now. Take a look at that. It's going to be n factorial. Where do I get the n factorial? Here. That's n factorial, right? Take a look at that. And if you take a look at this guy here, okay, n minus, which is going to be w. Don't forget we have a w here, right? So this is w. That's what we're plugging here, factorial, right? And the remaining 1 factorial is basically this guy. Look at that. Then multiply by this. So which is what you have here. Look at that. Okay. So that is what we mean. So that is the So if you take a look at this now, okay, this is a multinomial PMA. This is a marginal, okay? So just want to take note of that. Now, if you want to go conditional, okay, we can decide to find what is the f of y1 up to yj, giving yj plus 1 to that. You're actually going to use the idea, remember the other time that we're doing f of x given y, it's going to be f of xy divided by f of y. You remember that? Okay, so which means we basically do going to combine all this, which is going to be from y1 to yk, and the join. Note that y1 up to yk. That was why you have that. Okay, divided, don't forget, divided by f of that. Don't forget. You remember, if I have f of y given s, is basically going to be f of xy divided by f of x. You remember? Okay, so that is what we're using here. So here we are finding marginals, okay, and that is what we actually work out, okay, that we are able to arrive at what we have here now. So that's just theory. You can look at that and see whether will be able to derive that, but we're using the idea of conditional probability. Okay, I think I'm going to move to another set of multivariate distribution. And the next one I want to talk about is multivariate normal distribution. We just talked about multivariate, Bernoulli. Multivariate Bernoulli is called the multinomial distribution, but we want to move away from discrete probability distribution to continuous one. And we are visiting normal distribution. Okay, now there's something that we call a standard multivariate normal distribution. Okay, when you take a look at this guy now, okay, this is more or less we're using the idea of independent again. If Z1 follow, Z1, give me 1 second. Z1 follow standard normal with 0, 1. Z2 also follow standard normal with 0, 1. If Z1, Z2, probably up to Zn, okay, are independent, then we can write the joints. The f of Z1 up to Zn, okay, is basically going to be the product of the respective one. What am I trying to say? Okay, for this guy now, the f of Z1 will be 1 over square root of 2 pi exponential raised to power Z1 squared divided by 2. Okay, that's for Z1. Okay, for Z2, okay, it's going to be f of Z2 equal 1 over square root of 2 pi exponential raised to power Z2 squared divided by 2. Okay, it goes like that. And that's the reason why this is a generalization. Look at that. So what you're seeing here is just a product of that. Okay, now if I talking about the product, if I'm going to write this one in n time, this is a way to write that guy in n time. Okay, you have 1 over square root of 2 pi raised to power n. That's what it means. And this guy here is basically 2 pi raised to power minus half raised to power n. Okay, what is it going to give? That will be 2 pi raised to power minus n over 2. That was how you have that. Okay, now, and this, if you want to write this guy in n term, you're only going to introduce a summation. That was why you see a summation there. Okay, you're like, I have exponential raised to power x, and I want to write that in n time, and x is a variable. It's just going to be summation x. Because don't forget, es multiplied by es multiplied by es. Okay, in n time, it's going to be sum of what you have. Don't forget when you talk about exponential. Okay, now how can I write this in matrix form? If I want to write z squared in matrix form, it's going to be z transpose z. That's what you see here. Okay, if I want to write that in matrix form. Okay, so take a look at that. Now, what I've just done here is just more or less trying to call this a multivariate, okay, normal, okay, trying to call that multivariate normal now. Now, you remember the other time we talked about location scale family in the under univariate. Okay, we are generalizing that to multivariate now. You remember we talked about, location, scale, family. I told you what location is. I told you what scale is. Okay, for location, you try to talk about the center of the distribution. Okay, but if you talk about scale, okay, probably you're talking about the deviation, okay, along the horizontal axis from the center, right? Okay, so I walk you through this the other time, okay, but this is in a this is a in a scalar form. If I want to write that in a multivariate form, what I have here, okay, I'm gonna write it this way. So here, instead of absolute value of a sigma, I'm gonna have a determinant of b raised to the power minus 1. Now take a look at this. If y equal to that for univariate, this is for univariate case. But here, this is a multivariate version. That's a multivariate version. And we're basically going to use a vector. Mu here is a vector. B here is a vector. X is a vector. Okay? That's what I just wanted to. So that's a multivariate version. So if this is a multivariate version of this one, then if this is if the univariate version of a location scale family is this, then the multivariate is going to be this. That's what I mean. Multivariate is going to be this. Here is a scalar, but here it is not a scalar, but a matrix. I wanted to know that. Okay, so the moment you know that, then we're working with a vector now. Y will be a vector, mu will be a vector, b will be a vector, s will be a vector. So take note. Okay, then we can look at the mean of y and the variance of y. Okay, so if you go by what we've done before, expectation multiplying that, okay, this is going to be mu, then b expectation of x. And why do we have mu? We basically have mu here because this is actually more or less going to go to 0. Okay, you remember we did something like that before. And the variance of y, okay, we basically going to be this. You could just need to take note of that. Now, if I now want to apply that for normal now, the transformation y equal to mu plus bs has to be invertible. And the only way it has to be invertible if and only the matrix B is invertible. This particular matrix is invertible. That is the only way the whole thing is going to be invertible. Okay, now in which case the PDF of y now, I want to rewrite this normal distribution here in a multivariate form here. This one here is for standardized multivariate. That's a standard multivariate normal. But if I want to write it, I want to write the one that is not a standard one, the conventional multivariate normal. Okay, this is what I'm going to have. This is the way we normally write it out. Okay, that's a formula. That's a standard. Okay, so take a look at that. Where the variance of y is this guy. Okay, and the transpose of the inverse of this and this, we basically we're going to be that. We said something the other time, b has to be invertible. We're using the knowledge of matrix here. And don't forget, we talk about the determinant of b inverse. Okay, so it's in the formula here, right? Okay, so determinant of m inverse is this guy. And what is your m inverse? The m inverse is actually the whole of this. Plug that in here, and automatically it's going to lead us to this. So you can use your knowledge, you can revisit your knowledge of matrix for that. So that is a multivariate normal. So there's another thing that we call spectral decomposition. Okay, any square matrix M has a spectral decomposition given as this. Okay, and where D is a diagonal and O is the orthogonal, and which means if I use the matrix O to multiply the transpose, it's actually going to give me an identity. Okay, so this is just a theory. Okay, that you can just, and then we can define a symmetric matrix M. It's positive definite if we have this. All these are definition that you just need to, try to familiar yourself with. Okay, they are just kind of definition. You can actually read them up. Okay, you can read them up. But I'm gonna walk you through an example in a class tomorrow, so you can just read all this up. They are just for you to get yourself familiar with. Okay, so if you look at what we're doing here, if M is symmetric and positive with the spectral decomposition, m is going to be equal to that. If I want to find the square root of that, okay, this is what I'm actually going to have. And here we observe that this multiplied by that is basically going to return in m. Don't forget, if this is this, okay, and I want to multiply that, it means I'm actually having this multiplied by itself, and that will actually lead us to m. So you can revisit your matrix knowledge. Okay, I think every other thing here is what we've done before. You can just get yourself familiar with that. So I think that is a remainder of this, material. We're actually going to start deck 7 tomorrow. But before I start deck 7, I can walk you through some example. Is there anyone who need a clarification before I go today? Is there anyone? Oh, somebody has a question. If you have something like p equal to 0.3, is 0.7, is 0.5, is 0.8, then couldn't you have more than 1x be 1? You know, the reason for somebody who chat with me of is 0.3, 0.7, is 0.5, is 0.3, that is not going to be possible. You know why? Addition of the probability must be equal to 1. I'm going to say that again. Addition of the probability is just like 4 people that contested in an election. Okay, their addition must not be 100% of those who voted. So if a candidate A received 40%, maybe candidates is 0.3 or 0.2 or 0.1, when you add them up, that should be 1. We should be 100%. Okay, you get what I mean? So they cannot be, if you add them up, they shouldn't be more than 1 probability. You get what I mean? Somebody who shot with me. But let me tell you this, it's either this guy win or not, or this guy win or not, or the guy that have this vote win or not, or the guy that have this vote win or not, depending on the election rule. Whether you want to use the majority rule, there are different criteria to determine winner in an election. But what I can just tell you is just like in a multinomial distribution, all the probability must added up to 1. So for somebody who chat with me that talk about 0.3, 0.7, 0.5, 0.3, when you add them up, they will be more than 1. And that is going against the rule of probability. I don't know if I've answered your question. Somebody who chat with me. Okay, so I want to appreciate everyone for attending my lecture today. For those in my 5101 class, in the next 1 hour, all results for midterm 2 will be posted. Okay, all results for midterm 2 will be posted, and that will affect your grade. Okay, is there anyone who need clarification before I go today? Is there anyone? Okay, in the absence of question, make sure you stay safe. Okay, thank you too. Make sure you stay safe and have a lovely day. So bye for now, everyone.